Okay, now in addition to all this, we know Newton's laws, right? Okay. Now, if we combine this, as we talked about last time, with the equations of motion, you get for kinetic energy theorem. Where okay? Yeah, that's a big deal. Okay? And it applies to the labs you hopefully have analyzed. That should really get to me. Okay? Because everything we're doing is connected to those labs. And you need to understand what you observed with your eyes, your hands, set up, relates to everything else. So this analysis of your lab is critical. That and problem solving. The lab technique is important too. And how do you get good results? We haven't addressed that in any formal way, but we're going to be seeing, because we're going to repeat a lot of these experiments with better instrumentation, or with instrumentation that's fancier that maybe doesn't give us better results. Okay. And how do we know this? Well, that's what we did with the cards and the paper clips. Paper clips over the edge and card hair pulling and so forth. And I got John's analysis of that. For some strange reason, it didn't turn out to be as linear as it should. Well, and that comes down to probably, I don't have an explanation for that. I have a lot of very plausible explanations. I think I know what probably did it. It's just the systematic errors in timing. Okay? Did you really call the start when that pendulum hit the end? Okay? And would it not be more appropriate, because it's hard to tell when that thing actually comes to rest, if you find a feel of the rhythm. So you can do pretty well with that, okay? But maybe when the pendulum swings through its equilibrium position, which is really easy to identify. So you line that equilibrium position up with something and you just mark, right? You count each time that happens. That might improve the results. And there were bad results, I mean, but there's clearly you got a curve. And clearly, there's at least one and maybe more than one systematic error. Also, you were just observing this to the nearest count, or to the last count. You were doing the observation of where the thing was on that last count. It was never exactly at the stopping point on that last count. Okay? And when you get down to something that's only taking 4 or 5 counts, you got a pretty significant uncertainty. We need to analyze that, which we can't do until we get the analysis. Okay, right, so get that to me. Okay, good. So, anyhow, we've got tentative evidence for this. I don't think you've overturned, over 3 centuries of physics with that experiment, because we have to take certain possible anomalies into account. We have to try to correct them without going to electronic methods, the most accurate of which is record the waveform with a sound here and a sound there, and a microphone equally spaced, so you have blips that are accurate to about 10,000th of a second. Okay? And then you see how linear this thing gets to be. And there are other things in the equipment. There might be some in that puller that doesn't have much friction. That friction might not even be proportional to speed. You know, we make the assumption that it is, but it really isn't. Pretty close. Okay? Close enough for most applications, but no. Are the wheels nose good? No, the cars have pretty low friction wheels. Okay? What about the surface? Well, that's pretty sophisticated 21st century material there. Legs of the table, there's a problem. Okay, because I got them up in blocks that I cut with a miter saw. Okay, yeah, we're cut real precisely, so the table probably has
plus or minus the 16th, right?
Not that close, but that's okay. I can always set the table on the floor, but the floor's not engineered all that accurately either. Okay? And we could, of course, do some leveling, you know, put some kind of mechanism under the legs and do that. And so there are all kinds of things you can do to confirm or disprove this. Nobody is going to accept your current disproof. I don't even accept it, and I don't think you do either. Because it's a pretty crude set of measurements, although you all did a good job of doing it. They're unavoidable systematic errors. Okay? So I'm going to put down here we haven't done much with them statistically and stuff, but there be uncertainties. Okay? Like here, there be monsters. Well, in physics, there be uncertainties.
Will you have a fun explanation session of quantum physics? What you think?
No way.
How and why? How and why it changes?
No, we're not going down to the quantum level on this.
Well, no.
Now, second semester,
curious.
we should work out the quantum nature of the atom and how it's related to spectra and all that stuff. That's actually pretty easy. We can dispose of that in about one session.
Why does it change so
Why does
much?
what change now?
The physics in relation to size.
Because everything is at the level of probability when you come down to the quantum level. Okay? You never know when that electron's going to jump from one orbital to another. You never know when this reaction is going to occur. You never know when that nucleus is going to decay. But you know if you've got 10 to the 20th nuclei, you can estimate to within very small margin of error how many are going to decay today. Okay? Depending on the half-life of the nuclei. Okay? Or in the next second or whatever. Okay? You can pretty accurately estimate how long it's going to take 10% of them to decay, or 1%.
So it's kind of a matter of we can't observe well enough, we can't measure well enough yet.
Not just that, it comes down to the fact that when you measure something, you reckon. We haven't studied waves, okay?
There's no good
You got probability
non-destructive way to
waves
measure.
that exist in a superposition of states. You don't know what a superposition is, just like you add two waves, just like adding the curves for two graphs, okay? And these are complex valued functions, but when you observe it, this part of the superposition gives you one measurement, this part of the superposition gives you another measurement. When you measure it, it collapses into that one superposition. That's called the collapse of the wave function. Now, until we study waves, not going to make a lot of sense. Okay? So, but one thing I like to do at the end of the semester is do unit on modern physics. Okay, modern physics is now over 100 years old, because it's not that modern anymore. And the recent stuff is really weird, okay? Still, we can't get very deep into quantum mechanics, Bell's theorem, and stuff like that. And, you know, I don't know quantum mechanics at a deep level. By the deep level, I mean, you know, all the equations. The governor, I mean, you spend a lifetime. You specialize in that area, you spend your whole lifetime getting a handle on that and then trying to answer questions that haven't been answered. And I didn't go that deep into it. I mean, I could do matrices. Solve Schrodinger's equation for a hydrogen atom. Nobody can solve it for anything much more complicated than a hydrogen atom, or a particle in a box, that kind of stuff, okay? So I don't have a deep knowledge of quantum mechanics, but more than enough to confuse you guys.
Good.
And hopefully enough to enlighten you a little bit. And I can't talk with authority about all the weird stuff, okay? I'm aware of it. I kind of know how it's worked out, but I haven't worked it out. So I don't really know. Okay, anyhow, that's, okay, so we got a little off track there. Shouldn't have mentioned that. It's a good question. Okay, so we have this, and then we have pictures of forces. So we have this picture. Which you should be able to draw at least as quickly as I am, as I'm drawing it. And then maybe even some picture force. So you know what the net force is. So that F net is this. Or you have a pendulum. Small displacement, not even necessarily as big as I drew it. And you have gravitational force. I'll go label these, we've drawn these before. You have this. We set up our coordinate system here, and we've got this, which is pretty much equal and opposite to this, and this is pretty much equal to this. So the net force is this, and you have two similar triangles, length here, displacement, or distance from equilibrium here, and you have a vector picture. And these are similar triangles, etc. Okay. And I didn't write down omega equals square root of k over n, because everybody knows that better than anything, right? You know where that comes from in the derivation. You do the derivation, you see where it is, you see why it is, you see why it has to be. You don't necessarily do the derivation, but you know what the solution is. You plug it into the differential equation and verify that it works if omega is the square root of k over n. Okay? Derivation, you know, you officially want to use techniques of differential equations or uses exponential trial function. Find out that you got an e to the imaginary number times omega, which gives you what it gives you, okay? And hopefully you understand that. That's important and it's going to continue to be through your studies, okay? Euler identity and all that stuff. So, it's probably something I'm leaving out, but let's talk about how these things apply again, okay? Now they apply to the problems I assigned, okay? Everything that I've assigned you can do with what I've just written down on the board. But you have to know how to sort it out, and you have to know how to think it through so you can put things into the form of these equations. You have to have an intuition for the physics. Pretty obvious why, for a given mass, you have more acceleration if you got more force. You can feel that, okay? Just try to accelerate, so take a bowling ball, get a little acceleration, get a little more acceleration, just play catch with a bowling ball for that, you get it. Okay? Now, you won't be able to prove that it's a direct multiple of it, okay? It's linearly related. You kind of did that with the experiment we did last time, okay? Is it got to have an intuition about why these things are so you kind of get the feel of a situation rather than just pulling a bunch of formulas off the shelf and trying to put them together, which is, if you get into a complex enough problem, fatal. Okay? It doesn't have to be very complex. It's like you got a formula for velocity that applies to simple harmonic motion. You don't want to apply that to something that's in uniformly accelerated motion. You don't want to use equations of uniformly accelerated motion to analyze a simple harmonic oscillator. Yet people do. I'm trying to preempt that, okay? By giving you this framework and making you aware that there are different kinds of motion. But you have to work out problems. And you have to get familiar with, equations of simple harmonic motion. They involve a little bit of trig. It shouldn't give you too much trouble. You might have to do a little review, okay? And if it gives you a lot of trouble, if someone is giving you trouble, we'll talk about it a little bit, okay? Give some guidance. The problem you can't do because you can't do the trig, ask about it, we'll work it out, okay? Okay, so anyhow, there's where we are. So let's look at some of the situations again.